All right. Well, I hope everyone had a good weekend. And um, we're just about to dive into the discussion of how to go from metered computation to reversible computation and debugging, and to look at that, look at some of the issues there. So let me start a screen share. And I think that's the one. I'll do that. Okay, can everyone see the screen?
Yes.
Okay, yes. Okay. All right, so that's the code for metered computation. Obviously, this is just a toy. It's not intended to be production, but it gives you a rough idea. We walked through the code last time. But there's one thing I want to be clear about, which is this parameter step, right? So this parameter is coming in from the outside, and notice that every operation uses the parameter, right? So in particular, these just this just passes it along, but these three all use the parameter before taking any action, right? So that means that there is contention on this parameter, right? So this thing is outputting on the parameter, and all of these are receiving from the parameter. So what this does is that it outputs a fresh return channel, and so the return channel is not in contention, but the step channel is in contention. So everything is in contention with the step channel. And that does that make sense? Does everyone see that?
Yeah, so if we want to pause, the execution step should just stop producing.
Yeah, for sure. But I'm trying to raise a point about the global nature of the step channel, right? So what that means is that all threads, every thread of computation has to go through this thing. Right. And that is exactly the same. That's the same issue that is why the cost accounting introduces a slowness in the execution, right? Because all threads have to go through the cost accounting.
I see.
Right.
I mean, it's in real world scenario, this is not like a real problem, right? Because we have like just a number variable inside the concurrent store, and
well, we've done as much as we can to optimize, but if you didn't have to have locks on that channel, or if you didn't have to run all threads through communication on a single channel, it would be even faster.
I see.
Right? So you have contention on that thread. On all threads have contention on the cost accounting communications, and they could be a lot faster if there was no such contention. All right. So the issue is, to what extent can you get by with something else? So, and in particular, suppose that you have if we're trying to do reversible computation, what we're going to do is we're going to at this line, and this line have to be modified, right? This one we don't care about, right? This is, it's clear, right? It's just passing the par through. So it's, it's this line. So here at this point, we know that we have to basically store this thing before we run it, right? So we're about to output it, so we also have to store it. Now, if we store it at a global variable, then we also have contention at the global variable. What could we do instead?
I mean, the par is the only place where we know that starting on contention will happen. Until this point, we know that we have only one thread, right?
Well,
I'm just saying that
you don't know what context this is being decoded in, right? This may be part of, this may be happening in the context of a par.
Yeah, I'm saying that if we don't have the par, we definitely, we still don't have like another thread.
Yeah, sure. That's
so,
there. Hang on, looks like.
I'm thinking.
Okay, so the it's not about the par, it's about this channel, right? So
I'm thinking.
what could you do to use a different channel?
I was now first thinking about the metered execution.
Mm-hmm.
I mean, we need some kind of coordination, right? If we want to maybe prevent execution without enough phlogiston.
Yes, I agree. So with metered computation, you can't avoid it. So I'm not going. I'm not going to ask that we improve metered computation, or not demand that we improve metered computation. There's a possibility to improve it, but not by much. But you can see that you run into a similar issue. So you can think of all of these return things, right? Every single one of these has the same form. Output on the return channel, the encoding of the subsequent piece. Right? That's really what's going on. You're saying, I'm going to hand to the return channel the thing that we want to run. Right? So if we get some phlogiston and a return channel, then we've eaten up the phlogiston. Okay, so we got rid of the phlogiston, and at the same time we got the continuation that we need to go run. So running this equals eating the phlogiston, right? That's essentially the nature of this encoding. Is that clear? Okay, all right. So but notice this is equivalent to storing, right? Each one of these is like storing. So if you just did a par where you stored the thing where you copied this action, but you stored it somewhere. Now, if we store it in a new channel, right, then we can't get it back unless we remember where we stored it. Is there something we could do instead?
I'm thinking about encoding that you presented, where we create instead of just using the new channel, we push the previous channel. So some kind of linked list.
You could do that. You could absolutely do that. Yes. Right. So what you're saying, so the way I would do what you're suggesting is I'd have a second parameter here, right, which is the channel, and then I build up a new channel starting from some seed, right? And then I would and then every time I hit, I'd use the seed to build up the next location where I'm going to store something. Right? Okay. So go ahead.
The seed is the seed can be just like increasing the number, or
you could do that. You could do that. But there's something important about rho, and this is what I said the last time we talked. What's different about rho from pi is that pi, the new construct in pi, this is global, right? And anytime you want to communicate something like this anytime you invoke the extrusion law. So let me bring up. I guess I can go. Let's see. What's the best way to do this?
Oh, so new in pi is like similar to this step in the metered execution. It's like it must be synchronized.
Sort of. It's like the least amount of synchronization that you can get away with, but yes. So let me do. So we're going to make a new document. Hello, there we go. Okay, can everyone see this? So this will be our Scratch document. Okay, so this is our Scratch. So Casper Scratch calculations. All right, so anytime we have something of the form new x p, right, and for grins, I'm gonna write it this way so we're super clear, and then we put this in parallel. Now let's imagine this is probably not big enough. Let me
There we go.
Okay, is that visible?
Yeah, that's better.
Okay, so let's imagine that as a condition that the free names of P intersect with the free name, the free names of Q is equal to, say, U at a minimum, okay? And let's also imagine that P is equal to U bang star X. Oh, I'll say I'm writing in pi. U bang X in parallel with some other process.
So U is not a set of names. This is concrete name.
Right. So I've just said that there's a set containing U.
Okay.
Right. And then further, let's also imagine that Q is structurally equivalent to for Y from U Q prime. Okay. So those are our conditions. So now in this expression, it's clear that P and Q can run, and that it is also, if we didn't have the new scope around P, and if we just had P in parallel with Q, they could run. It's also clear that the new scope doesn't bind U, right? Doesn't bind the place where they can interact. Yes? Okay. So that means we're free to use extrusion, right? So we can now do new X. Let me run it this way. P par Q, right? So I've now had to extend the scope of Q. So if in a distributed computation setting, P is running on one machine and Q is running on another machine, then this scope now has to be recorded on both machines.
Mhm.
So the new scope just keeps eating and eating, right? It gets bigger and bigger.
I see.
You never run it this way unless you can prove that X is not mentioned in Q. But if X is shared inside, if there's the possibility of a communication, right, that where X gets shared across that communication, then this scope just expands and expands. So in this way, this is so if we're returning to our desire to talk about quantum mechanics, this is a form of entanglement. These two systems are entangled because they share a secret. But it's a kind of hidden variable entanglement, right? It's not the weird sort of distributed correlation that you find just using the quantum mechanics. This is a hidden variable approach or view on entanglement. It's a shared secret. All right, so go ahead.
Can I just mention that this looks like if someone is using X inside inside function, for example, and now we are like parameterizing and we are saying, oh, but now we will put this parameter for this function, but also whatever scope we have.
Yeah.
In a sense, this is a
same as threading a parameter through a bunch of functions. Yeah. Yeah, that's exactly right.
So Dan Cornely was saying how he's arguing that in OCAP's way, we always want to push I/O on the top level.
Oh, that's bullshit.
This is,
sorry. Pardon my French.
Yeah,
that's just not.
So I wanted to ask you. I was thinking this is not compositional because we will end up on the top level. We will have everything on the top level.
Yeah, it's not. Yeah, that's clearly a non-starter. That will result in non-scalable systems.
Okay.
Greg, I have a question.
Sure.
I thought the main difference between rho and pi was the capability to construct names with processes. And
yes.
Yeah. Okay.
Yeah. So that's exactly what I'm about to get to. Okay. Right. So the new gadget is fundamental to pi. Right. It's like pi is not Turing complete if you drop the new constructor. And that's easily proven. I strongly suggest you prove it for yourself as an exercise.
And is the reason that we cannot create any more a new state?
That's correct. Basically, it's a Turing machine with a finite tape.
Oh, makes sense.
Yeah. Okay. So with rho, we have this fact, right? So the fact is that at P, I don't want you to do that. Thank you. At P, all right, we know that this is the case, is not in the free names of P. That's a fact that you can, that's a little lemma that you can prove. Okay. So And again, I strongly encourage you to prove this for yourself. Right. So the fact that you can never have the code of P mentioned in the free names of P in standard row calculus or in rholang has an important consequence. The consequence is that I can always get something locally fresh to P. How do I do that? Well, I just quote P. Does that make sense?
Yes, but is this just one name?
Yeah. Once you have one name in a process, you're Bob's your uncle, right? Because I can always then do.
Oh, you're basically saying if you have the seed, if you have always the fresh seed, you can generate whatever you like.
Correct. Right. So I can always do this,
Okay.
right? I can always do this. And then now I have a process, so I can take the at of that,
Mhm.
right? And now I have a name, so I can, and so on and so forth.
Mhm.
And at each step, I know that they're all distinct, right?
So we are basically repeating the same thing as you described many times from start. From nil, we can generate all of the names, but now you have at P as the starting point.
Correct. That's right. That's right. So I can always get a fresh one in any given. So starting from a process P, I know that at P is fresh from P, and now I can generate an infinite number of names that are all fresh from P. Right. And so the point is that it's local, it's not global. Right. It might not be fresh from Q, but notice that if I want something to be fresh from P and Q, what do? I just put them in par, and then I take the name, the at of that.
Mhm.
Right. And so then so for any given code context, I can always make something that is locally fresh with respect to the code context. Does that make
Because
sense?
this
Yes.
context is basically giving us the seed.
That's correct.
The context itself, the structure of this context is basically what is different or unique.
Yes. Yeah, exactly. And so what could we do in this setting? Right. So let's go and copy this. Right. So let's do it in 2 steps, right? So step number 1 is we want some store. Yes. That's where we're going to record. Right. And the problem with the store. So I'll just go ahead and put the parameter in all of the. So the problem with the store is this is global, right? So so as a first, and again, let me just so that we have a little bit more room. I'll clean this up like this. Okay, so that's that definition. Okay, and then there's that one. Just so we have some room to mess around. It's like we're pair programming. Okay. So what we're doing here is converting metered computation to reversible computation. Funny story. I was once trying to make this point to the Fields medalist, Michael Friedman, who was working at Microsoft on quantum computation. And I was trying to get to this level of conversation, but he couldn't understand the definition of pi. So we got hung up on just trying to describe what pi is, so that we could get to the point where I could talk about how you can use how you can build reversible computation automatically in a calculus like this. Okay, so our first approach to this, right, is not very happy, but it's something we could do, right? We can do this, store, and then this has to take the store in the recursive call, and this has to take the store in the recursive call. Right, so here we're doing the metering part and the storage part. But yes, is that clear?
Yeah.
Okay. So and we know this is wrong, but we're just like proceeding in steps.
I was thinking that you will supply store as a parameter to step. So that step will execute and store.
No, that turns out to be more work than needs to be done.
I see.
Okay, so obviously these are incorrect because the arity is incorrect. So we're just fixing those up, yes? Okay, and then here we're just going to do exactly the same thing. So, well, let me fix this up first. And then when I copy it, I won't have to fix it a second time. Finally, by the third one, I figured out. Okay, so now you can go to the store, and assuming that really what this does is instead of overwriting store, right, it collects them in a queue, right? That's something. Right. So as a variant, right, we could, so I'm going to avail myself of let, right? And everyone agrees that let is just syntactic sugar, right? I don't have to explain how let is derived. Okay. All right, good. So I'm going to avail myself of a let. So hopefully this code is now readable, right?
Mm-hmm.
Okay. So how about we do let in store, that's the new store, be the at of P in parallel with star store. Does that make sense? In fact, we should do the whole thing. I'll do all of it. Does that make sense? Right? All we've done is do a let so far, and now we're going to use it. And how are we going to use it? Well, in every recursive call, we want to use the end store, right? And then here. And now it's localized. Does that make sense?
Oh, I see. Yeah. So the computation that we want to store is part of the channel.
Yes.
Store. Okay.
Exactly. Right. And so now if we know the seed, we know the salt, then we have the form of the program, we can always go and recover where it was stored. Yes.
Interesting. It is interesting that a very similar thing I suggested to Will just a few hours ago, how we can store a dispatcher together with the original contract.
Yes. So exactly. It's a very similar idea. So now we see how this is done, right? And the rest of it is completely automated. So this is in store, and this is in store. There's no cleverness in this. Trying to avoid cleverness.
Oh yeah, this is nice because we are not using some kind of structure like a list, which can be like a huge if we are debugging huge program. And...
Correct. Yeah. I mean, I think there's some not so nice things, but so this one we have to be a little bit careful about. But yeah, that's we can optimize this away and just do that. Yes. Okay, and so then this becomes in store, this becomes in store, and this becomes in store. Okay, so now we have something that is both metered and reversible in the sense that we can always go find what we were about to do, right, and recover it. We know where to go looking to go and run things backwards. We have all the data necessary to run things backwards.
Mm-hmm.
And
store channel, yeah, and store channel can be maybe another shard, for example, because we want to we don't want to put debugging data in our main space.
So for example, that's a way to organize things. Yeah, you could, and so then this thing could be the seed that gets you over to the other shard, right? That's what that's the namespace that puts it in the other shard.
Nice.
And again, it fits on a single page, right? So conceptually, it's very simple. I mean, and we've done all kinds of, configuration here, right? We've in the sense that like we've pretty printed it, and it still fits on a single page. And the value of being conceptually simple means that it's easy to prove properties about this, right? So notice that rho is conceptually simple. And because it's conceptually simple, it allows us to easily prove important lemmas like this one, which then give us the ability. So this lemma is what's giving us the ability to know that this code here is correct. Does that make sense? Okay. Right. So and likewise, because this is conceptually simple, proving properties about this encoding is similarly simple. The proofs are easy, and that's basically what me being a bear of very little brain. That's what I need. I need things to be very simple so that my proofs are like not super hard to do. Okay, so I did your homework for you. I was hoping that someone would have done the homework so that we could then do cup and cap. But we can do cup and cap next time. So hopefully people got something out of the conversation today. Okay, all right.
And
good.
For the proof, I'm thinking the easiest way is just to use what rholang is already giving us from the perspective of structural equivalence, and do we need even something else than structural equivalence?
So before you have a proof, you need to make a crisp statement. So what you want to do is you want to say something to the effect that for any given process that can evolve. You can also run it. You can go back to a previous state. So for any given process P, if P goes to P prime, there's a way to go from P prime back to P, right? And that's essentially that's essentially what's going on. So, and the way you do that is P prime will have P in storage. Right, when you go, right, when you go from P to P prime, you know that P prime will be structurally equivalent to an in-store bang P.
And how, if P contains and modify some other channels?
Good question. Good question. Yes, that's what makes the trick, the proof slightly trickier, but it's still doable. So, right. But the core insight is that whenever you get to a P prime, right, P prime will have all of the side effects, right? So just to be super clear, right, what we're saying is that
I mean, like I think about P prime as oh, I have the state hash, so I can go back to previous state hash, but maybe not something you have in mind.
Oops. Stop. All right. Okay. Then you have that P prime. It will be triple equals. I think it's in favorites. Here it is. Basically, you want to see yeah, we want to do it this way. Exists an S such that P prime is equivalent to S bang P par P double prime. Right, that's that you can prove, right? That's a little lemma that you can prove from this definition, right? And that's just obvious, right? It's like, because all you do is you do it by induction. Is that clear?
I'm not exactly sure. Can you scroll down and
So you have to be a little bit careful about the parallel composition, but apart from the parallel composition, this is obvious. Yes.
What is S?
So S is going to be our store, right? So I can find there is a channel such that P prime is equal to some channel where I have stored P as my original state, and I have some other side effects. Does that make sense? So just take a case, right? So here's a case, right? So in order for this to evolve, it can't look just like this. It has to be an X and a 4X, right? So you have to be a little bit careful, right? You can see what the issue is. You have to have a bang, an X bang, and send and receive on X, right? In order for this to happen. But what that means is, so as stated, it's not quite right because of this thing about par. But you know, if you restrict this to just these cases, then what you can do is you can split this into a P and a context K, right? Oops. So we're going to restrict P to be one of the cases, one of these cases. So this case, or this case, right? And then what you want is that K of P. You see what I'm saying? Right? So this, then you know that there is some storage here and there's some P prime. So in this case here, in the 4, or let me use the output, because that way we can have both on the same page. This can't evolve by itself, right? It has to have some context K where there's a 4. Okay, so P is going to be the output. K is going to be something involving a 4 on X. And so then that evolves to a P prime. So that means that in order for that to happen, right, we will have had to store the P, right? We can't actually run the output without storing the P.
Mhm.
Right? So therefore, this has to be lying around somewhere, and this is whatever the rest of it is. Does that make sense?
Yes. And how we can restore the when we want to go back in reverse?
Well,
How we will remove?
good question. Good question. How would you do that?
I mean, we know what we executed. We have this in store.
Yeah,
we
but
cannot
notice that,
somehow.
yes, you can, because notice that this is the junk that's left over, but all of that junk is, I can apply this lemma to that junk as well. So if I just run this all the way to ground, right? So either it loops, or, you know, along, either it terminates, right? In which case, every little piece of it is stored, or, and I know the sequence of steps. Why do I know the sequence of steps? Because inside this storage, I have recorded every single step. So I can piece the execution trace back. Does that make sense?
Yes. But
Okay.
how to restore? Mhm.
So now I just go ahead and run the thing all the way to completion, and I can use the structure here to say how all the pieces are related to each other, and I just unwind them. And if it doesn't terminate, then I know that for any loop point, I can do the same thing. And if there are no loops, then I just, you know, along any depth on any branch, I can run it backwards. Does that make sense?
I'm not sure that I understand how you run it backwards. Are you saying you're not really running backwards, but you start from
what I'm saying is, inside here, I have all the structure I need to relate. Let me draw it out this way. It'll be easier, and then we have to stop because it's 8 o'clock. So this part is also going to turn into one of these.
Yes.
Right? So it's going to be a P double prime and an S prime, right? And then this will be a triple prime, right? And so on and so forth. So until, let's just say it's a terminating process until we get to 0. But now notice that I can also, it's not just a par, because all of these have inside them this structure here.
Mhm.
So I can reassemble the execution trace by looking at the names.
Yes. So I mean, are you saying that instead of directly doing like a reverse, we start again, but we stop one step before that we want to reverse?
No, I'm saying that we can construct, we can construct the reversal. That there's enough information to construct the reversal.
And this means that we are somehow executing a COM event which will produce the
Whoa.
state before this COM event.
Remember that if this is the case, then I have a duality, right? Since this is the output, this has to be a 4. And so now I can construct a new K and P prime, a K prime and a P prime, where the output is the context for the 4. And so I have the same thing for the context that I have for the process. So the 4 will also have an S and a P somewhere in this mix. So what I'll have is I'll have the top level.
I see.
Right? So I'll have both the output and the 4 store. I'll have an S and a T, which has both the output and the 4. And so they'll be there. And so now I can reconstruct the K of P. I can go all the way back to K of P. How do I do that? Well, I just simply, there's going to be one that is that is basically only the store, right? And nothing else, with no additional information. And then we probably it's better to use it will be more convenient if we roll this back by 1, right? So we do the store and we would use the in store, right? So then we don't have to worry about the boundary. But I mean, you can do it either way. So then there'll be an S which has no additional context, and that's our top level. And there'll be 2 of them. How do we know that there are 2, or at least 2? Because there's going to be a 4 and an output, right? And so then I know that everything else is subsequent, right? That these are all continuations of the behavior. So I know exactly what the top level is by looking at the structure of S. And so then I can reconstruct K of P. Does that make sense?
I cannot say that I completely understand, but I need to think about it. Can I just ask you, I don't want to prolong, but you mentioned that there is duality. Can you just point me on the place where should I think more?
So yeah, so just think about it, right? If I'm doing an output, so this is some output like that looks like that, right? So if P looks like this, then we know then K looks like this. Oops. And then, there's some K prime here, if that's where the hole is. So there are 2 possibilities. So either K looks like this, par some K prime, or K looks like this. Because we're only talking about one hold context. Okay. Is that clear? So therefore we can also do this. P R is equal to this, let's pick this one because it's slightly simpler. Let's fill in 0 here. Right? P is equal to, sorry, K prime. Is equal to X bang Q tar, and then we put the hole there, right? So I can now apply the lemma to where I've switched the roles, right? I changed what was the process, what was the context into a process, and I changed what was the process into a context.
Mm-hmm.
You see?
I see.
Now you have to be a little bit careful. This 0 is not quite right, but the main point is that in order for this to go at all, this has to have one of these two shapes, right? Because it has one of these two shapes, well, we know therefore that when we run it, we're going to do this one, right? And so therefore there's going to be another S, right? Not this S, but some S, or call it T. There'll be a T, right? Where the input thing is stored. So now I have the output thing and the input thing, and they're at the top of the tree. There's no additional context sitting at S, right? Because every time I make a recursive call, I add more structure to the storage channel. Yes, right? But these two, the P and the K, they don't have that structure because they're at the top of the tree.
I see. And are we storing K also in the store?
But that's the point. That's what I was just saying. K has to be, either this shape or this shape. And so I can apply the lemma to K where this becomes the context. And so therefore, this thing is also going to be stored somewhere.
I see. I'm a little bit constrained by thinking, on another side is the whole R space. We cannot store it.
No, this is not the whole R space. This is just the context in which P is running. We're just using the row calculus. We're not doing rholang, but it works for rholang as well. It's just that, it's like K is just the R space is just K. So, and you're perfectly free to treat it that way. But the main point is this thing is stored somewhere.
Okay. I think I now understand. But basically, you're saying we can reverse because the context is whatever is the rest. Because we know the part that will match, and whatever is the rest is the K. So we can go and revert to that other thing.
I mean, literally, I'm just to be clear, right?
Okay.
In order for this to happen, K must either look like this or it has to look like this. We know if it looks like this, then we know for a fact that will be stored somewhere. Yes?
I'm concerned about K. I mean, K can be very large number of.
It doesn't matter because we'll just recursively apply this. It doesn't matter how large it is. Right? We didn't say that it's necessarily going to be computationally compact or efficient. We just said that we can do it.
I see. Okay.
Right. So, and we know we can do it because this is going to be stored and this is going to be stored, and the same is going to be true for K prime recursively. Right. Right. So everything that's at the top level will be stored, and it will be stored at a name which doesn't have any extra structure in it. And so therefore we can pick out the top level And therefore we can get back to, we can reassemble this thing from all the top level storage slots. Does that make sense?
Okay. Yes. Yes. Thanks.
Right. So that's the math. So again, very simple lemma, very simple induction, and that's I mean, there's literally no conceptual trickiness here, right? And that gives you a proof that this will give you all of the reversibility, right? And it's automatic, right? This is we algorithmically get reversible computation from, so someone could write ordinary row and we can automatically transform it into reversible row.
Yes.
Right? That's kind of important. All right, we're way over time, sorry.
Thanks.
Thanks, Greg.
Sure.
Thanks. Bye-bye.